In this video, we're going to talk about Hooke's law. We'll go over the momentum principle again, but this time for a variable force, and then we'll cover inclined planes. And we will apply this to a problem involving a spring on an inclined plane. And we know that springs are prevalent in society. For example, the coil springs that you will find on the shock absorbers of vehicles. And so it's important that we understand how these springs operate. Remember that a force is any interaction that when unopposed will change the motion of an object. And so remember we talked about the four fundamental forces of nature. We talked about Newton's three laws of motion, friction, which is opposition to that motion. We have electric and magnetic forces as well. We have buoyancy. We have centripetal force. We have gravity. But today we're focused mainly on springs. And so for springs, we have Hooke's law. And Hooke's law gives us a force function which is dependent on the elongation of the spring. And so the elongation S is represented by the final length of that spring minus whatever the initial length of that spring is. And so we have, for example, here we stretch it S, and then we could also stretch it 2S. And the more the elongation, the more the force. And so the more it's going to want to get back to its equilibrium position. We also have a negative sign here along with a L hat unit vector to give us the direction, indicating that it's a restoring force. And so the force is directed towards the equilibrium position, trying to get back to its resting position. All right, and so now we'll go over momentum and impulse. Remember that momentum is just mass times velocity. As the mass goes up or the velocity goes up, that momentum will go up. It is a vector. We can break it into its components. We also could give a unit vector to our momentum. We also have this idea of impulse, which is anytime you have a change in that momentum. And so remember, though, that if your force is varying, then we need to actually look at the area under the curve. But a lot of times we like to approximate that with some average. So imagine a rectangle, which is basically the same area as that curve. And then we kind of can avoid calculus and make some assumptions here. And so what we can do is we can assume that the net force, therefore the acceleration, is constant over small enough time intervals. And then we can do this update process, which is somewhat tedious for humans to do repetitively, but for a computer program like Python, we can do these updates very, very quickly. And so we have this idea of a momentum update, where you're just looking at the momentum a short time into the future. And so it's this idea that your velocity is changing. It comes from the Newton's second law, which basically is looking at how we can connect force to a change in momentum over time. And then we can basically say, hey, that's our momentum principle. And just remembering that we actually should be integrating, but we're kind of approximating here with a assumption. But we can rewrite it like this, and we can look at the final momentum equals the initial momentum plus whatever net force you have times the change in time. The other way of getting to that is just looking at the change in momentum and getting to that same place. We can also divide it by mass, get to this formula right here, look at it in terms of a velocity update, so to speak, and then we can kind of turn that into basically just a change in velocity. And so we're really looking at changes in velocity or acceleration here due to some force, whereas we can also do a position update. So once we know the final momentum or final velocity, what we can do is update the position. And so now we have a change in position, and so what we'll do is just kind of look at that change in position and say, okay, well, that final position is going to be equal to whatever the initial is plus my average velocity times the change in time. And we can also get to that formula by just looking at that change in position. And we can also rewrite this average velocity in terms of momentum. And so this makes it nice because we can just change this in terms of momentum, and then whatever we get for our momentum update, we can plug it right into the position update. And what makes it even easier, which we're going to find, is when we have a variable force, what we can do is, instead of writing it as an average of this initial and final momentum, what we can do is make the approximation that we can just say, okay, well, this average velocity is just dependent pretty much on the final velocity if the time steps are small enough with a variable force. And so What we can then do is rewrite this as the final momentum over mass with this approximation for a variable force. And this makes it really easy because all we have to do now is find the final momentum with this momentum principle. Once we know the force and the time and the initial momentum, once we have that final momentum, we just plug it directly into the position update, divided by mass, and we got our position update. And so that's very nice for us to be able to do that. Inclined planes are important simple machines to consider. And so what we basically have is a ramp with some angle with respect to the horizontal. Now what we can do is put a mass on that ramp and then consider the forces acting on it. We can consider gravity acting straight down, and we can consider the normal force acting perpendicular to the surface. We could also consider friction, which would be opposing the motion, but for now let's ignore that and assume that it is a frictionless surface. And so the next step would be to assign a coordinate system and say, how are we going to analyze the position of this block with time with respect to some origin? And so we could come up with a coordinate system like this where we have left and right and up and down. However, it's going to be a little bit tricky to monitor the position of this mass in 2 dimensions when all we have to do really is tilt the coordinate system, and now we only need one coordinate to describe the position on that inclined plane. And so we tilt the coordinate system to match the angle of the incline. And now, if you notice what happens, the normal force does not need to be broken up into components. However, the gravitational force does. And so we have this interesting situation where we actually do have to break gravity into its components, and so we have a component acting into the ramp and a component acting down the ramp. And we also can know that this angle here is going to be equal to the angle of the ramp. And so when we find that, we can do some trig, and we can break it up into our components, and we say acting down the ramp is mg sine theta, into the ramp is mg cosine theta. And so we basically understand now that the y dimension doesn't really matter because the net force is going to be 0 in that dimension. And so the only thing that we really care about is this mg sine theta down the ramp. And so for this situation, we have a net force of mg sine theta negative, and that just indicates that it's down the ramp. And so comma 0, indicating that there's no other net force in the y or z dimension. All right. Let's apply some of these concepts to a problem here. And for this one, we have a mass of 10 kilograms attached with a spring here, and that has a stiffness of 120 newtons per meter. It's attached to the top of the ramp where there's a wall, and it's a slippery ramp, so we're not going to consider friction. The relaxed length of the spring here is 1 meter, and if we need to use the gravitational acceleration due to the force of gravity, instead of using 9.8, they want us to use 10 meters per second squared. And they're also saying at a time t equals 0, so when we're starting the stopwatch pretty much, that its length is going to be 2 meters, and so it is going to be stretched a little bit to start off. And it does have some initial velocity here in the x dimension of -1 meters per second. And so for this, we have part 1, and we're going to use a time step of 0.02 seconds, and we are going to find the momentum and position after 0.06 seconds. And so one of the first things we have to do is draw a free body diagram. And so when we do that, we'll find that the spring force is directed upward because we know that it's actually on the way down the ramp, and so the spring is really trying to get it back to its initial position. Its unstretched position, which is 1 meter, and right now we're 2 meters down the ramp, and we're on the way down even more with our initial velocity, and so our force is going to be directed upward. And we have a normal force, which is going to be perpendicular to the surface. We have gravity, which is going to be straight down. And so what we can do now is look at what the system in the surroundings is going to be. And so for this, we could say, okay, well, the system is going to be our block, and the surroundings will just be pretty much everything else. So the earth, for that gravity, we have the spring, and we have the ramp providing that force, normal. And so what we also can do is look at the principles and concepts we're going to need to solve the problem. And so we are going to use that momentum principle that we learned earlier and update that position as well with that iterative process. And so we'll see how that works. And we also have to make some assumptions. We are assuming, as we just said earlier, that this slippery ramp does not have friction. And so we're also assuming that there's no drag force. And we're assuming that this is non-relativistic. In other words, the velocity is much, much less than the speed of light. So that gamma is going to be about 1. And we also can say, okay, well, the time interval 0.01 seconds is short enough so that the force is essentially constant. And in this case, they actually 0.02 seconds. So we're basically saying, hey, the time step that we use is pretty much good enough, all right? And even though the force is changing, we're using a small enough time step so that we can assume that it's constant. And then we also assume that, again, this time step is small enough so we can approximate that V average is approximately equal to that final velocity, as we saw a little bit earlier. Solving the problem is going to be basically broken up into 3 parts. And so the first step here, we have 0.02 seconds. So that first time step, we're going to consider the gravitational force, and so what's going on with that? Well, we know that this is a right triangle, and we could find that angle there and break it up into mg sine theta and mg cosine theta, and we could use the angle, but we could also recognize that this is a 3, 4, 5 triangle, and so we could find that just basically by using the Pythagorean theorem. 3 squared is 9, 4 squared is 16, 16 plus 9 is 25, the square root of 25 is 5. And so we have a 3, 4, 5 triangle, and we know that the mg sine theta, well, sine theta is going to be opposite over hypotenuse, so that'll just be 3/5, and cosine theta is going to be adjacent over hypotenuse, which is going to be 4/5. And so gravity acting down the ramp is going to be negative mg sine theta being 3/5, and negative mg cosine theta being 4/5 is going to be acting into the ramp. And so that's what gravity's doing. We're trying to get to this net force. We need to consider the other forces. Well, the spring force is going to be acting in the positive x direction. And so we know that depends on the elongation. And they told us that it's stretched to a length of 2 meters, and the initial, relaxed length is 1. And so we got to do 2 minus 1, which is 1 meter. And so we know that the spring constant times the elongation is basically going to give us our Hooke's law, and which is going to give us the strength of that spring force. And we know that the constant is 120, and so 120 times 1 is just 120 newtons. So we have 120 newtons acting up the ramp, and we have negative 60 newtons acting down the ramp. And it's basically this battle between the spring and the gravity for the position of that mass. And the only other thing to consider would be the normal force, and the normal force is acting with the same as the mg cosine theta, but in the opposite direction. And so instead of negative 80, it'll be a positive 80, and so that dimension cancels out in terms of net force. And so we finally get to this net force basically just being in the x dimension. And again, we have that battle between gravity and the spring force. And at this time, the net force is 60 newtons up the ramp towards that wall at the top of the ramp. And so what we'll do is we'll apply this momentum update. And now that we know that force, that net force is 60, all we really have to do is say, okay, well, let's look at the initial momentum, which is just 10 kilograms times that initial velocity, which is that negative 1, is traveling down the ramp initially. It's traveling down the ramp, but the net force is actually up the ramp, and so it's actually slowing down. So we're going to add this net force times time term in. We just found the net force, and we'll add that time in there as well, and we'll multiply those together. We end up with a final momentum of negative 8.8, and so we know that there's some negative momentum at the end of that time step. And so we'll update that position, and we know it's going to be a little bit farther down the ramp. That's what we suspect, and it is. And so instead of negative 2 down the ramp from this coordinate system, we're actually going to be a little bit farther down the ramp, so we'll be at negative 2.0176. We got that just basically by plugging in that final momentum, making that approximation. in here and dividing by the mass, multiplying it by that time step. And we also considered the initial position to be -2, so that's important. So we know that it's stretched to be 2 meters, and we know that that's in the negative x direction. So we're actually considering a -2 to be our initial position. And so make sure that you're aware of that. And so now we'll move on to step 2. This is a summary of what we had from the first step. We have our net force that we calculated, our final momentum after 0.02 seconds, and our final position after 0.02 seconds. And so what we'll do now is consider what's going on in the next time step here from 0.02 seconds to 0.04 seconds. And so we know that the spring is going to have been stretched a little bit more. It's still moving in the downward direction. But now we have more elongation of the spring, and so more elongation means more force. And so what we'll do is we'll find that new elongation to be a little bit more than 1. And so when we multiply that by that 120 newtons per meter for the strength of the spring, we'll get something a little bit greater than 120. And so we got 122.1 newtons instead this time. And so our gravity and our normal force are going to be pretty much the same. And so we have this new net force, which is going to be a little bit greater than 60. And so it really wants to get back towards that relaxed, unstretched position even more now. And so what we'll do is we'll do a momentum update, and the final momentum will be equal to the initial momentum, which is the final momentum from the last step, plus the new net force that we just got, times that 0.02 seconds. And so we end up with a final momentum of -7.5577. Notice how that is just a little bit less in magnitude than what we had before. In other words, it's slowing down. So it's still moving down the ramp, but the net force is in the upward direction. And so we're kind of slowing down as we go down the ramp, and we really don't want to be going down the ramp anymore due to our net force up the ramp. And so we'll plug that new final momentum into our approximation for the position update. And so we'll plug it right in there. And so we do that, and we get a -2.0327 meters approximately as our new position. And so notice how we're a little bit farther down the ramp now than we were before. Okay. And so this is a summary of the first 2 steps. And we just need to do it one more time. So right now we're at 0.04 seconds. We'll do one more time step to get us to that 0.06 seconds. And so what we really need to do is calculate that elongation again, because we know we're just a little bit farther down the ramp. So we stretched that spring a little bit more. And so we're going to have a little bit more now. We'll have 123.9 newtons as our spring force now. And so that also changes our net force as well. But remember that gravity and normal force are still pretty much the same. And so our new net force will be 63.9 newtons up the ramp. And so it's wanting even more to go up that ramp now because we don't want to stretch that spring. The spring wants to get back to its relaxed position. And so we'll do our last momentum and position update here. And we'll use our information from step 2 as the initial information for step 3. And so for our momentum update, we know our final momentum after 0.06 seconds is going to be equal to whatever it was at 0.04 seconds, which is that -7.5577, plus that new net force that we just calculated times that time step. And so we have our final momentum now, which is pretty much the answer to our problem, but we also need the position. And so we'll plug this into our position over here as that PF, and we will end up with a final position after 0.06 seconds of -2.04527 meters. And so that is the first part of this problem. The second part of this problem looks at what would happen if you plugged it into a program like VPython to do some of this work for you. It'll become a lot less tedious because this iterative process can be done a lot more quickly. And so what we usually would do with these lines of code is start off by defining our variables. And so we have the mass to be 10, we have g to be 10, we're going to calculate that force of gravity in the x direction to be that -mg sine theta. We're going to have the spring constant to be 120. We're going to set the relaxed length of the spring to be 1. We're also going to set that position to be -1 in terms of the unstretched length, because we know that our origin is at the top of the ramp. We know that our length currently at the beginning of the problem is going to be 2 meters, which sets that initial position to be -2. And so we know that the force of the spring, we got to kind of plug in the Hooke's law formula. We basically have the net force coming from the gravity and the spring along that x. Remember, we said it was a battle between gravity acting down the ramp and the spring acting up the ramp. And so we also can set the initial velocity that they gave us to be down the ramp, so it's initially traveling down the ramp. And then we set the momentum formula to be mass times velocity, pretty much. And then we set the time step to be 0.02. We initialize the time at t equals 0. And then we basically start this loop. And it's calculating the new spring force, it's calculating the new net force, it's calculating the new momentum, and it's calculating the new position, which is that momentum and position update. And then you also have this line where we increment the time by the time step. All right, so that's how you would comment on this line of code. And then part B is asking, if you read the output of the program, what would you need to focus on to figure out the maximum stretched length and when it occurs? And so eventually, when this block continues to go down and down, it'll eventually either reach the bottom of the ramp, or the spring will break, or at some point this spring is just going to be so overwhelming that it's going to stop here, and it's going to then come back up the ramp once the spring force becomes great enough due to the elongation being great enough. And so what we would look at is we would want to find out when the position vector r begins to decrease again. And we can do this by finding out when the velocity changes direction. And so going from positive to negative, or negative to positive. And so we know the velocity is down the ramp. And so once that velocity changes to be up the ramp again, we know that it's changing direction and it's reached some sort of a maximum point. Part C is asking, what adjustment would you need to make in the code above, right here, to find the exact point in time when the block was at rest. And so we would need a smaller time step to find out when the momentum becomes 0, basically. And so the smaller the time step, the more accurate you're going to be. And then we're basically looking for when is that momentum becoming 0, and then we know it's at rest. All right, so that's how you would work this problem or think about this problem in terms of coding. And I hope that the idea of a spring force, a variable force, is making more sense now. Gravity working on an inclined plane, hopefully that makes a little bit more sense now. And using that momentum and position update, hopefully that makes a little bit more sense now, especially when we can use that additional approximation for a variable force. And so we'll see you in the next one.